So I'm a postdoc in a team in CA, Grenoble. So I will be presenting not so much work, but rather reflections we've had on how, in our community and more especially in our team, we want to tackle the Exascale challenges for our codes and maybe for others also. So bear with me and keep in mind that this presentation concerns my community and may not be relevant to absolutely everybody. So I will be presenting the challenges we feel we face on the road to Exascale and how we want to answer it by using modularity and portability of HPC applications. So why do we need Exascale platforms? To solve larger problems, to have paradigm shifts, problems we couldn't solve before, to publish more paper, more or less, for many, to make economies of scale, because building one big machine is more economic than building several small ones, to fuel the industry, and to keep computer scientists occupied, because else we might start doing crazy stuff. But the problem is that all those goals are not compatible. For instance, publishing more paper faster means you don't have time to refactor your code. So you just jump on a new platform and get some hours and run something which is not optimized. So it's not economic. You're not making economies of scale when you do this because you're underutilizing your resources. So this is the second point. Same thing for the industry. They want results now. They don't want results in 6 months or 2 years. It's not economically viable also because computer scientists are paid to optimize codes on new platforms every time, and again and again, and several times they optimize several different codes which all implement the same formalism. But each code has to be optimized in its own way. And then there is the problem of physicists talking to computer scientists, and usually it does not reach comprehension. We have a different way of thinking, and it needs a lot of talk to get things going. So, and what is the problem? The problem is this. So this is the top supercomputers in the world from the past 5 or so years. There are some other exotic architectures in the mix which have appeared, but they were never number one. So these are the number one architectures of the top 500 for the past few years. And they don't look like any of them. They are all different. And the question is, what will we get tomorrow? And those are some, maybe guess, someone just for fun, but ARM plus DSP and Intel Atom plus FPGA are something which could happen. Maybe not will, but could. So how should we program adaptive applications in order to be able to populate all those platforms? So why are scientific code of limited portability? Mainly because they are huge, hundreds, thousands of lines. They are written in Fortran, which is especially agile language. They are mainly collaborative efforts, so you need to gather a lot of people around if you want to change something in a big HPC code. You have many different programming paradigms, meaning you need a lot of expertise in order to be able to touch those codes. MPI, OpenMP, OpenCL, CUDA, and so on. FTI. And the question is, how can we make this application portable? So what I will be talking about today is modularization and module reuse, composition of those modules in order to build an application from basic building blocks, maybe using domain-specific language. So this is for the portability part. And the second part is getting those things efficient. So I will be talking a bit about what we think of autotuning for libraries and how runtimes can help you tune application at the top level. So first, modularity. So I will be talking about our code here as an example, and it will be following me during the presentation. So this is a split of the big DFT functionalities in terms of what are the library we are using. And we still need to break down the big DFT block on the top into several smaller modules that we need to use. So we need to assemble all of this to make a big DFT-like application. Just to give you an idea of the kind of architecture we are looking at. So, how can you glue this little library together? Because this is a problem. Usually physicists use Fortran, but and Fortran is very nice for a lot of reasons, but it's a bit difficult. So what we try to do at the lab is that when we extract a library, we provide a DSL with it, either to be used directly in the host language, Fortran for instance, or a domain-specific language that would be able to generate the final code rather than write directly in the target language. We are trying to go to task-based programming with data flows and so on in order to take care of the node part of an application, so at the node level. And at the top, we are currently looking at component-based programming in order to assemble the different algorithms which can compose our executable. So, an example of low-level library we are working on is libconv. So the idea is that we want to, the basic building block of big DFT, the formalism is Debussy wavelet. It's unique to this application, or it was unique to this application, but nowadays it's starting to pop up in other applications. But nonetheless, there is no library to implement this formalism. So we built an Autotune library based on Autotuner Boost to provide those functionalities and to offer them to other people who would like to use this formalism. And we are working currently on a DSL to prototype application based on this formalism. And the idea is that at the end, the DSL will be able to generate your application. We are working on algorithms which are at the intermediary level. So we're working with an American professor, Eric Polizzi, on an algorithm which is FEAST. And the idea here is to provide this algorithm in the form of a library with task-based parallelism, and where you can substitute the blocks which this library uses. For instance, the Hamiltonian application, you can use the one of big DFT now, or you can use the one your code provides. And the idea is to provide, so this was done in Julia, this experiment, and the idea is to provide a library of different algorithms which are tuned for our community, where you can put your own implementations in the bottom, and that you can use as an algorithm inside your application. So the idea is that the algorithm should be taking care of the algorithmic part and not of the implementation of the low-level routines you should be providing. So this is for the node level, our vision. And at the top level, we are working with Christian Perez of INRIA to break down big DFT into components that we can then compose, like the different algorithm and the data repartition. And we are designing this DSL with Christian in order to get a component model to rebuild big DFT from the basic blocks directly, and abstracting the parallelization of the program. So this was for the modularization, and for the performance portability, because it's nice to be portable, but if you don't have performance, it's not very useful. So we are developing Boost, which is an auto-tuner, because all codes are not based on BLAST, LAPACK, and FFT, unfortunately. So we propose a dedicated Autotuner where you can describe your own formalism. And the example here is libconv. Thanks to Autotuning, we can generate the basic routines of big DFT, but in fact, we can cover a whole lot more kind of routines. For instance, we can implement all the Debussy wavelets, which was families, which was not possible at the time. So there are many new experiments we can do in the code, like reducing the wavelet precision at the first steps of the program, and then increasing it. We can reduce floating point precision because now we have simple precision routines. We could even try half precision routines if we wanted to. So we have a whole lot more opportunity to optimize our codes than we used to have thanks to autotuning and metaprogramming. And we can generate Fortran C, OpenMP, CUDA, OpenCL. So choose your poison and we can provide it. We are going for task-based programming, and what is the interest of task-based programming in terms of optimization? Especially in the run times, because the abstractions of the task are very well defined. So it's entirely possible to get a good vision of your application, and it can be introspective, meaning that the runtime knows how long a task will take based on previous execution of these tasks, so it can make educated scheduling decisions and load balancing. So a very good example of this is a couple of programs which are in the POP Center of Excellence, which are StarPU plus SimGrid. So I directed the PhD on this subject. And these two tools are used in linear algebra, and with meaning that you couple a runtime system for task-based application with a simulator, and then you can faithfully predict how long your application will take given the parameters you've chosen, the scheduler you've chosen, and the system you're looking at. Meaning that we don't need to do experiments anymore on the scheduler in StarPU. We just simulate it and we say, okay, with this we will get 25% improved performance without running the code anymore. And it supports hybrid architectures, so you can run it on CPU plus GPU or CPU plus accelerator in a more general manner. And the last point, what is the pros of using component-based models for our application in terms of performance? It means that we can have a data flow description of our algorithm, and so we can transparently test different repartitions of data or different algorithms which take different data repartition as input. And the component runtime is responsible for gluing these together. So a lot of the complexity is gone. It can be useful for fault tolerance, although, but I will not talk a lot about this. The only real problem with that, it's not really production ready. So there is still some research to do on these topics if we want to use them for the Exascale. So we'll go to the conclusion. So how does these tools help us solve our initial problems? Well, the structural change we wanted to do on the first are much easier if our application is programmed this way. So it kind of answers the question of number one. If you spend less time developing your application, you spend more time doing physics. So usually physicists should be happy about it. It allows to better target your efforts on the important libraries, especially if you share them among codes of the same community. And so you better spend your computer scientists' time and your money. So the 4 is almost the same as the 2, faster results. And cost prediction is useful if you can simulate your application, because you know how much your result will cost you. And don't worry about computer scientists, we'll have some work to do. So perspectives. So we are working on modularizing BigDFT and creating material science libraries. We would like this movement to gain some momentum. So we think that co-designing libraries between developers of the same community could help a lot to have those components reused in several codes. And so we are working currently on DSLs in order to prove that this kind of approach can be very efficient for prototyping. And we are working with Christian to develop those component-based approaches, which are quite new in the HPC field. They've been used for a long time in distributed computing departments, but for HPC it's quite recent. And this methodology can be applied everywhere, so we'd like to discuss, of course, with those interested. So we are working, so I'm not directly working on this. It's a PhD student, last year American PhD student, so a 5th year PhD student, and Luigi Genovese, who worked for the past months on this subject. So they took the direct FIST algorithm for Professor Politi, they binded it in Julia, and they proposed callback so they could replace the Hamiltonian evaluation inside of it, and then they use directly the FIST algorithm. But the interest of the FIST algorithm is it's directly parallelizable, but it was never done. So in this way, they managed to parallelize it at the component level, if I remember exactly. Exactly. I'm not expert on the subjects, but apparently they were quite satisfied with the results. So, but if you want, you can write to Luigi Genovese, and he will be very glad to have these discussions with you, I'm sure. It is already packaged this way, meaning that when you download the BigDFT application, all the libraries which are presented at the top, they are given to you in forms of source, and you have one unique building script which builds all the library and links them all together. But what we would like is to distribute some of those libraries, and some of the libraries we will be creating, to have them incorporated in other codes, and incorporate libraries from other code inside BigDFT. So we can provide more functionalities. And it will also help with the reproducibility of our results, especially in DFT, where there are lots of papers on do the code compute exactly the same values for such and such parameters. It would be much easier to be sure what we're doing if we're using the same basic building blocks for the community. So. Yes, there is a lot of rich algorithms landscape, so yeah. No, no. There are certainly guidelines, but certainly not rules. So it may depend on your application. It may depend on the needs of the different applications. That's why we are talking about co-designing these blocks with the community. So we have a library which fits more or less everyone's need. Because if you do your library for your needs, nobody will use it because obviously you forgot the needs of somebody else. So it was interesting that developing the code with Eric Polizzi's student because Eric Polizzi doesn't have the same needs as we do. So we had to take everything into account. And so I think the interface is richer this way than it would have been if we had only developed it ourselves. So that's why maybe we should discuss what kind of components we want to come out of the community which could be useful to everybody. And so when the time comes to port this application on an Exascale machine, we don't have to optimize every single integral, Gaussian integral code everywhere, and maybe can share a common code base.